Welcome to Lecture 8 of the Wireless Communication course. Today we will talk about OFDM. First, we will look at where we are in the course. So we've seen already a good part of the course. So we first talked about the wireless channel in the first few lectures. We talked about path loss and shadowing, and then about multipath fading in narrowband and wideband. Then we spent a few lectures on how to optimize performance and to assess performance over the wireless channel. So we had one lecture on the communication performance, where we saw that when you communicate over, for instance, a really fading channel, you have a big penalty compared to the additive white Gaussian noise channel. And then we talked about two ways to improve performance. One was diversity, where you basically send the same thing multiple times and then do coherent combining. The other one was water filling, where we try to make best use of the resources that we have, given knowledge of the channel at the transmitter side. So these techniques, diversity and water filling, can be applied in different ways. And to see this, we will look at three different technologies or approaches. One is OFDM, next time multi-user communication, and finally MIMO. And this will then lead into the last part of the course, which is on more advanced topics such as 5G and localization. This will be the topics of today. We'll talk about single and multi-carrier modulation, and then we will have different mathematical components that we'll go through in detail, and in the end we will see an OFDM transmitter and receiver. The text for today refers to chapter 12 of the book, and I recommend, as always, that you read the highlighted sections. Specific learning outcomes for today, we will talk about the need of multi-carrier modulation, the drawbacks and benefits of analog multi-carrier, the use of DFT for OFDM, diagonalization of circulant matrices, how to design an OFDM system with certain requirements, determine the overhead of cyclic prefix insertion, and also talk about some of the drawbacks of OFDM. Before we go into OFDM, we will first briefly recap last lecture. So last lecture we talked about rate and power adaptation. The idea of all of these is that you adapt to the channel. So you assume at the transmitter that you know what is the current channel, and then you adapt based on these channel conditions. So the first one we saw was rate adaptation, where we essentially shrink the size of the constellation when the SNR is worse, and then use higher order constellation when the SNR is better, without changing the power. We saw also power adaptation, which tries to keep a certain SNR at the receiver and does this by increasing the transmit power when the channel is bad. And this power adaptation turns out to be a very poor strategy. And then finally, we saw rate and power adaptation, which can be cast in a so-called water filling problem, all of which relates to solving this kind of convex optimization problems, where the variables are x, k, and these typically refer to the power that you allocate on a certain channel k. And the solution is always of the same form. So the allocated resources on channel k are a maximum of 0, and then something called 1 over the cutoff value minus 1 over the available, somehow the available SNR on that channel. And this BC is used to make sure that you meet this equality constraint, which makes sure that you meet either the average power constraint or total power constraint. Which constraint matters depends on the setting, and we've seen two cases. One is statistical water filling, where you allocate power at each time, where you make use of good channels by using more power, and bad channels to use less power or no power at all. And here you should meet an average power constraint, so you can allocate a lot of power now and less power later. We've seen this water filling interpretation, where the amount of power we allocate relates to the water level here, and the water level can go up or down based on how much average power we have available. We've also seen another case which is called deterministic water filling. In this case, at each time you have a certain number of channels available, and you need to allocate power to those channels subject to a total power constraint, so not an average power constraint. Optimization problem turns out to be of the same form as before, but of course a solution of the same type as before. Now the picture is a little bit different, but again, the amount of power that you allocate depends on the water level. You can change this water level, which is this red line, up or down when you have more or less total power available. If you increase it, then the total amount of water increases, so you will have more power to allocate. If you reduce it, you have in total less power to allocate. So now we've seen how to use the wireless channel in a better way. Today we will see how we can push performance even better. In particular, we want to go to higher data rates. So we want to push our data through faster. How we can do this is we can either send more bits per symbol or reduce the duration of each of the symbols. Sending more bits per symbol is good, but it is limited by the signal to noise ratio. You recall that when you have higher number of symbols, then you need a higher SNR to meet the same, for instance, bit error rate requirement. So this is limited by basically the transmit power and how far the transmitter and receiver are apart. On the other hand, you could reduce the duration of each symbol, but this will lead to intersymbol interference, because by reducing the duration, you're increasing the bandwidth, and when the bandwidth goes over the coherence bandwidth, you will have intersymbol interference. So this is what is shown here. At the transmitter, I have these distinct pulses, 3 distinct pulses, but if these pulses are too long, if these pulses are too short, they will blur together here, leading to intersymbol interference. Good. How you would deal with intersymbol interference, there are different ways. One is to use equalization. And we don't see this explicitly in this course, but equalization considers basically filtering the received signal and then removing decisions of previous symbols to avoid this intersymbol interference. Typically, this is challenging because either the performance is bad or the complexity is very high. And different kind of equalizers will have complexity ranging from linear all the way to exponential. And for those of you who've taken the digital communication course, this exponential increase comes from the Viterbi algorithm that you run on the trellis of the channel. So rather than sending the symbols faster, what we can do is we can split our spectrum. So let me go back. So here what I did is I have this whole frequency band and I allocate either one single carrier stream where I send the symbols very fast. What I do here is I create many channels that are operating with very low bandwidth, but they're all operating in parallel. So I split my spectrum into non-overlapping channels. Each of the channels has a small bandwidth, so you're sending symbols slowly, so they will probably be flat fading. So you don't have any intersymbol interference within each of these channels. Now to do that, you need suitable hardware at the transmitter and the receiver. So this could be one architecture where you have your received signal here, then you down convert based on the carrier frequencies of each of these channels. You have an analog filter, you sample at the symbol rate, you have demapper, and then you convert, you combine the low rate streams into a high rate stream. Now, this is a bit challenging because as you also can see in this picture, you need a guard band, right? Between each of these channels, you need a small guard band, and this leads to loss of spectrum. And in communication, probably the most precious resource you have is spectrum. That's why operators pay billions of krona just to get a few tens of megahertz of spectrum. So for that reason, there was enormous interest to have more efficient and especially digital implementations of this multi-carrier scheme. And this dates back from the 1960s, where it was developed in Bell Labs. And then in the 70s, the ideas of using an FFT, which stands for fast Fourier transform, and cyclic prefix was introduced. And the idea is, as an analog multi-carrier, you create parallel sub-channels, but you make it fully digital with a highly efficient implementation, and you avoid intersymbol interference through something called a cyclic prefix. And we will explain all of these in detail. The mathematical components to understand these are these 4 puzzle blocks. So we'll talk about discrete Fourier transform, circular convolution, diagonalization, and tuplets matrices. Our first topic will be the circular convolution. So we've seen already a few times standard convolution with a discrete time channel where you have an input corresponding to times n. You have a channel with certain taps, so here n means delay from 0 to L, for instance. And then the output at time L is the convolution of the channel with the input, and is given by this expression in discrete time. So the output at time n will be the channel at delay 0 with the input at time n, the channel at delay 1 with the input at time n minus 1, and so forth. And sometimes this is written with a star. And even sometimes you will see this written as h star x n to show that the output is computed at a certain time n. Now, circular convolution is a special case of this where the input is periodic. So the input has a certain period, let's say n, This is what this colored picture shows. So I'm sending the same data many times with this period of length n. So this implies that the input at time n is the same as the input one period later. So all that matters to describe the signal is one period. If you know one period, you know the whole input signal. The channel is as before. It has L plus 1 taps. Now, when you have a periodic input and a fixed channel, then the output will also be periodic with the same period. So the output at time n is the same as before, but now since the input is periodic, we can add or subtract capital N here. And this is sometimes written with this notation, with the convolution symbol with a circle around it. In MATLAB, the circular convolution is implemented by the command cconv. So circular convolution is nothing more than a convolution with a periodic input and a periodic output with the same period. So here's a simple example of convolution and circular convolution. Let's suppose that you have a channel with two taps, 1 and minus 1, 0.5 at these delays. You have this input preceded by zeros and on all sides. And I ask you to write down the input-output relationship in matrix form for standard convolution and for circular convolution. So you can take a small break, otherwise we go on. So the simplest way to do this is you just compute like y0 is, and the standard equation, h0 x0 plus, let's see what were the delays, 0, 1, 2, h1 x n minus 1 plus h2 x n minus 2. So this is this standard convolution. I can put in here any value that I want, so I can change this to n, and I already wrote n here. And if I then compute this, I find that, well, these are my inputs. This is x. I create a vector of this. This is the outputs that I will generate correspondingly to each of these inputs. So that I call this a vector y. And then I can rearrange the channel coefficients into this matrix. And this matrix I will call H. And you see a kind of nice structure in here where on the diagonal or you have this, and then on the off diagonal you have this. And this matrix in this case will be a 4 by 3 matrix. Right, and you see the channel appearing in this column here. You can also see it appearing in this row here, right, in this direction or in this direction. Now, when the input is periodic, we can again compute the convolution just as before, and then we can write the input here as length 4. The output then becomes periodic as well, so we can write many periods of this, but the output will just be periodic, so we just focus on one period. We call this y, we call this again x. And now the channel matrix will be a 4 by 4 matrix, where again we see this on the diagonal and here on the off diagonal. But now we also see appearing this guy here. You see, and this is because of the circle, because of the periodic nature of the input. Due to, let me write it, periodic input. Right, this is because the output at the first time depends also on the inputs before this time, which were again 0, 2, 1, 1. This is why you have this minus 0.5. And I recommend that you do another example with this periodic input of length 4. So it has, this is the one period, second period, and another period. And again, try to reconstruct this channel matrix, and you will see that it has this structure. Now, these matrices have a special name, so this is called a tuplets matrix. And this is called a circulant matrix. Circulant matrix. And it's called circulant because you see each row or each column is just a shift of the previous or following row or column. Good, I think it's time for a break, so then we will continue back later with the discrete Fourier transform.